I provided copies of both the periodic table and isotopic table in the reference module of Canvas. These tables are very important, folks. They contain a lot of information that you need to solve the problems for the class. You must understand the structure of the tables and the information contained in the cells of the tables. So looking at the periodic table, the rows, so here I am identifying the rows in red. We don't call rows rows on the table, we call them periods. You also have columns, so the columns go up and down. Here I am showing them in purple, and the columns we refer to as groups. Now the groups on the table have been numbered differently at different points in history and different parts of the world. The way that makes the most sense for us in an intro class is to follow the naming convention, the numbering convention from about 20 years ago, and that is to label the tall columns with the numbers 1 through 8. You also have the staircase, this here, looks like a set of stairs, that separates the table into two halves, obviously not two equal halves. Metals on one side, non-metals on the other. You are familiar with enough elements to figure out which side is which. For example, iron, copper, silver, gold. All right, these are all well-known metals. So obviously metals are on the left side of the staircase, which means the non-metals are on the right side of the staircase. Now there is one exception, and that is hydrogen, which I'm labeling with an X here. Hydrogen is on the left side of the staircase, but it is actually non-metallic. There are some materials that are not entirely metallic and not entirely non-metallic, and those are the metalloids. And the metalloids are typically found at the intersection or at the staircase between the metals and the non-metals. Different references say different elements are metalloids. I went with something in between. But basically, if the name of the element is underlined, then it's a metalloid. So you can see the underlined names here: boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. So that's some of the gross or main structure of the table. There's more details talked about in the families document in the reference folder, but I want to zoom in on a portion of the table so you can create a sort of key. So I want to look at the boron box, right, on the left side of the screen. And I just want to be sure that everyone knows what information is where in each of the boxes. So the first thing you have is the number at the top of the box. And you'll notice that each of these numbers is unique for each of the elements. And that's because this is the quality that makes one element different from another. So the atomic number is what we're talking about, and it's defined as the number of protons. Changing the number of protons changes the identity of the atom. Now, it is true that atoms are electrically neutral. By saying that atoms are electrically neutral, we're saying that the number of positive charges is equal to the number of negative charges. Now, for that reason, it's generally true that the number of protons is then equal to the number of electrons. And because of that, students sometimes tell me that the atomic number is the number of protons or the number of electrons. But that is not correct. You cannot say that the atomic number is the number of electrons because that number is not fixed. It's very easy to change the number of electrons in an atom. As a chemist, it's impossible for me to change the number of protons in an atom. Maybe a physicist and their miraculous devices that they have, they can change the number of protons in an atom. But in chemistry, that just isn't available to us. So the atomic number is the number of protons only. You definitely have the name of the element in each box: boron, carbon, nitrogen, and so on. And then you have the symbol. Now the symbol always starts with a capital letter. If there's a second letter to the symbol, it's always a lowercase letter. So B for boron, C for carbon, N for nitrogen, all the way over here, Ne for neon, right? Some of the symbols make a lot of sense, and some of the symbols may not seem to make sense, and that's probably because the symbol is based on the Latin name of the element. And then you have the number at the bottom of the box. So 10.8, 12.0, 14.0, and so on. That number at the bottom of the box is the atomic mass. And that sounds self-explanatory, but I assure you it is not. So you would think that this is the mass of that kind of atom. And it's close to being that, but that doesn't quite do the number justice. Since the mass of an atom is dictated by the mass of its nucleus, because protons and neutrons are heavy and electrons are extremely light, you would expect all of these numbers to be whole numbers. And obviously, they're not all whole numbers. Now, one thing that's different on the table that I created for you is that all the masses have been rounded to 3 sig figs. We know the mass, or the atomic mass, of each of these elements to a great deal of accuracy, many, many decimal places. But that really is impractical for us to deal with so many places. So this simplifies the math and the rounding that we have to do by limiting everything to 3 sig figs. So what the atomic mass is something we have to leave off just for a little bit, and we'll definitely come back to that. So that's the basic information on the table. Now there is some additional information for the nonmetals that I gave you, and that would be this other number here that I'm highlighting in yellow, and that would be the electronegativity. I only provided that for the nonmetals because you just don't need that information for the metals. And at some point during the course, electronegativity will become relevant.